Hello, my name is Mário. I'm from Portugal and I'm studying materials engineering at the University of Porto. Today, I'm going to present you an ongoing work about the dissertation of completion of my master's degree in engineering. This study will focus on the fatigue performance of high-strength steel welded connections under a rotating bending fatigue test. First, I'm going to start with a small introduction and motivation for this work, followed by the methodology used for the specimens tested. Then I'm going to share and discuss the results obtained from the fatigue tests, and at the end, the conclusions and future works. Governments nowadays are aiming for the decarbonization of energy and the economy in order to achieve a more sustainable world. And for that, they are focusing their attentions on more clean and renewable energies, such as wind turbine structures. Since Portugal has a long coastal area, many of these installations are going to be located offshore. These structures are made from fixed steel sections connected together through welding techniques. And since we are talking about offshore localizations, there are some types of environmental cyclic loadings leading to cyclic stress, known as fatigue, and it's the main property that leads to catastrophic failure. Also, since we are talking about welding techniques, it's important to understand the three main sections of a welding connection. First, we have our base metal and welding material, which is composed of the filler material used in the process. And then we have the heat affected zone. The heat affected zone had some types of changes in the microstructure due to the heat input of the process, such as grain size coursing and secondary phase formation that leads to changes in the mechanical properties of the material. For the experimental part, two 30mm thickness plates of quenched and tempered S690 steel were connected together through metal active gas process, and Correia 69 was used as the filler material. From the welded plate, two main sections were cut, A and B, and from these two main sections, longitudinal and transversal cuttings were performed by abrasive water jet techniques. From each section, 24 specimens were extracted, being 16 of them for the base material, 4 for the heat affected zone, and the other 4 for the welding bead. Here you can see the technical plan and also the section A and B, and also the morphology of the specimens tested. As red arrows, it is possible to analyze the specimens from the heat affected zone, and as blue arrows, the specimens where the shortest sections intersects the welding material. The rotating bending fatigue test was performed under a fatigue stress ratio of -1 and a frequency of 23 Hz. Here you can see a schematic representation of the fixed location of the specimens on the rotating motor and also the added mass that will act as a submitted tension. Here is represented also the maximum bending stress expression used for these tests. The first type of results obtained from these tests is the Euler's curve, also known as SEN graphics, which correlates the number of cycles until fracture of each specimen with the stress amplitude applied. For this test, a 10 million cycle fatigue endurance limit was stipulated, so any specimen that reached this value was considered as a runout. Here you can see the mean curves for both slice A and slice B for the results obtained from base material, and by the determination coefficient here represented, we can prove that the statistical model will provide a good outcome of results. It is worth noticing that we have a small discrepancy on the results for heat affected zone and welding material for low cycle fatigue tests, and this discrepancy tends to increase for fatigue tests with higher cycles until fracture. Now, for the mean curve with the 3 different zones of section B, we can see the same problem for the heat affected zone and welding material as in the last section. But it's worth talking about 2 specimens that can be outlier. The first one is for the base material, and he's had some type of residual magnetism, possible due to the handling of the plate during the manufacturing process. And by the bibliography analyzed, it is possible to refer that the magnetism tends to increase fatigue resistance of our material compared to the other ones for the same stress amplitude. The other one is also for the base material and had lower fatigue resistance compared to the sample submitted to the same stress amplitude, and this can be due to some type of internal defect like inclusions, but only with further SM and AS analysis it is going to be possible to take more conclusions. Here you can see the results of all specimens compiled together for slice A and B. It is important to notice that tests for welding material and heat affected zone were only conducted for 2 different stress amplitudes, 520 and 480 megapascal, due to the limited number of specimens. For 520 megapascal, by dividing the mean and the standard deviation, we can see that results are very discrepant for heat affected zone and welding material due to the heterogeneity of the microstructure in these zones. For 480 megapascal, that doesn't happen because there was a higher number of specimens that reached the fatigue limits. Therefore, the results are not that dissimilar. The second analysis that we made was for the fracture surface analysis. And for example, for the base material, we can see that we have a nucleation site at the bottom left and another one in the top right that is possible, and it's possible to see a radial pattern diverging from these sites that represents a fatigue crack growth step. Here we have represented the final step, which is the catastrophic failure that is represented by a more fragile zone of area of our sample. And it's also possible to see a middle section with a different roughness composed of the so-called dimples. This means that the material went through some type of plasticity before the final fracture of the component. It is worth noticing also the difference in the size of dimples between the filler material and the base metal. And for the weld metal, dimples tend to be smaller and more stacked together due to its increase in ductility. To conclude, it is important to note that fatigue behavior highly depends on the high variety of factors that leads to result scatter, such as surface finish, residual stresses, and material defects, such as porosity and inclusions. The dispersion of results for the air affected zone and welding material are due to the heterogeneity in the microstructure in these two different areas, and also due to the irregular air affected zone area definition across the thickness of the plate. As for future works, we are going to analyze and compare the material microstructure with the fatigue behavior in order to investigate the effects of grain size, crystallographic orientation, second phase formations, and the hardness profiles. Also, we are going to evaluate the effect of the thickness size on the quenching and tempering treatment during manufacturing on a 60mm thickness plate of the same base material. At the end, we are going to compare the results from our tests with the ones presented in the standards. I would like to acknowledge this project, Asfalto da Licença Metalomecânica 4.0, and thank you for your attention.